step into the visionary world of Erich Hückel, the master builder who transformed our understanding of the microscopic realm. This narrative explores his pivotal role as the architect of quantum chemistry, a pioneer who bridged the daunting chasm between the rigorous laws of physics and the complex behaviors of chemistry. By applying the principles of the wave function, represented by the elegant psi, Hückel decoded the structural secrets of the molecular world, most notably within aromatic systems like benzene. Through his revolutionary insights, he provided the mathematical keys to unlock molecular stability and reactivity. Join us as we trace the legacy of a man whose theoretical bridge forever changed how we visualize and manipulate the very building blocks of matter. Welcome to the Scholarly Slate, where we examine the monumental contributions of Erich Hückel. A physicist by training who reshaped the landscape of chemistry, Hückel's legacy is built upon two intellectual pillars. In 1923, he co-developed the Debye-Hückel theory, applying electrostatic principles to decode the complex behavior of strong electrolytes. By 1931, he pivoted to the quantum realm, introducing Hückel molecular orbital (HMO) theory. This breakthrough utilized quantum mechanics and the famous 4n+2 rule to explain the unique stability of aromatic compounds and their delocalized pi electrons. By replacing empirical guesswork with rigorous mathematical frameworks, Hückel bridged the gap between physical laws and molecular reality, forever altering our understanding of molecular stability. Trace the evolution of a scientific pioneer in Hückel's intellectual path. We begin with the foundation in Göttingen, where young Erich first explored the nature of matter within his father's home laboratory. This empirical spark ignited a journey into the math, as he underwent rigorous training in physics and mathematics between 1914 and 1921 under titans like Peter Debye and Max Born. Finally, we witness a unique cross-pollination. Unburdened by traditional chemical conventions due to his lack of formal training, Hückel possessed the rare freedom to view molecules through a purely quantum mechanical lens. This distinctive perspective allowed him to revolutionize the field, proving that the most profound breakthroughs often occur when an outsider reimagines the boundaries of science. In Act 1, The Electrolyte Anomaly, we confront a classic scientific puzzle. Early 20th century chemists held the ideal expectation that strong electrolytes, once dissolved, behaved as independent ions in a simple, concentration-based system. Yet, the empirical reality proved far more complex. Observations of electrical conductivity and osmotic pressure deviated wildly from these tidy predictions. Why did these solutions fail to act ideally, even when diluted? This tension between theory and observation highlights the limitations of treating ions as solitary actors. We are witnessing the moment where empirical data demanded a new mathematical framework, a bridge that would eventually be built by Debye and Hückel to explain the hidden electrostatic forces at play. Witness the dawn of modern solution chemistry with the Debye-Hückel solution of 1923. Breaking away from the idea of random ion distribution, this theory introduces the ionic atmosphere, a neutralizing cloud of opposite charges that surrounds each ion, creating a vital electrostatic screening effect. The mathematical heart of this discovery reveals that the activity coefficient, gamma, the factor adjusting concentration to reflect true thermodynamic activity, is proportional to the square root of the ionic strength. This breakthrough replaced empirical guesswork with a rigorous, predictive physical model. By decoding these hidden electrostatic interactions, Hückel and Debye provided the first clear mathematical lens through which to view the complex behavior of electrolytes in solution. In this pivotal chapter, we encounter the Copenhagen catalyst. While studying in Denmark under a Rockefeller scholarship in 1929, Erich Hückel's path intersected with the legendary Niels Bohr. At a time when quantum mechanics had only just solved the single chemical bond, Bohr issued a daring challenge: apply this new physics to the mysterious carbon-carbon double bond. Driven by this provocation, Hückel made a radical pivot. He abandoned his existing research on adsorption and moved to Leipzig to collaborate with giants like Heisenberg and Hund. This shift marked the beginning of his quest to decode the quantum nature of organic bonds, setting the stage for a theoretical revolution that would forever change our understanding of molecular architecture. Welcome to Decoding the Double Bond, a journey into Hückel's 1930 breakthrough in molecular architecture. Before this insight, the nature of multiple bonds was a mystery. Hückel proposed a revolutionary sigma-pi separation, identifying two distinct orbital types. He envisioned sigma bonds as the axially symmetric, rigid skeleton of the molecule. Above and below this plane lie the pi bonds, delocalized electron clouds that act as a lock, explaining why molecules like alkenes cannot freely rotate. This conceptual division provided a vital mathematical shortcut, allowing scientists to treat complex conjugated systems in isolation. By distinguishing these forces, Hückel unlocked the secrets of molecular rigidity and established a foundational principle of modern organic quantum chemistry. We now face the benzene conundrum, a profound scientific mystery that challenged early chemical intuition. While Kekulé's classic model proposed a ring of alternating double bonds, such a structure should have been highly reactive. However, the thermochemical evidence revealed a startling reality: benzene released significantly less energy than predicted, only -206 kJ per mole compared to the expected -354 kJ per mole, proving it to be impossibly stable. This discrepancy raised fundamental questions. Why was benzene so chemically inert? And how could all 6 carbon-carbon bonds be perfectly identical in length? This tension between classical theory and experimental observation created a vital puzzle, inviting a new quantum mechanical perspective to finally decode the true nature of aromatic stability. Enter the year 1931, the moment Erich Hückel orchestrated a fundamental paradigm shift in our understanding of the microscopic world. In Hückel molecular orbital (HMO) theory, we witness the dissolution of traditional chemical boundaries. No longer are electrons tethered to specific atoms or bonds. Instead, within a pi system, they are liberated, delocalized across the entire molecular ring like a shared energetic cloud. By solving the complex Schrödinger equation using just two elegant parameters, alpha, representing isolated orbital energy, and beta, the resonance between neighbors, Hückel distilled the complexities of quantum mechanics into a predictable mathematical reality. This visual captures benzene's mystery finally unmasked, revealing a system where equality and shared energy define the very essence of molecular stability. As an outcome of HMO theory, we encounter the magic numbers, Hückel's famous 4n+2 rule. Here, the abstract becomes predictive. A planar, conjugated ring achieves exceptional aromatic stability only when it possesses a specific number of pi electrons. Visualize the electron parking lot of molecular orbitals. This mathematical formula ensures that every low-energy bonding orbital is perfectly filled, creating a stable closed shell akin to a noble gas, while leaving high-energy anti-bonding orbitals vacant. This explains the enduring mystery of benzene's stability versus the volatility of systems like cyclobutadiene. With this rule, Hückel provided the ultimate chemical compass, allowing us to distinguish the remarkably stable from the inherently fleeting in the vast landscape of organic molecules. In the culture clash, we witness a fundamental rivalry between Linus Pauling and Erich Hückel. Pauling's resonance theory captivated 1930s chemists with intuitive drawings of oscillating bonds, a brilliant but approximate heuristic. Conversely, Hückel's molecular orbital theory was a physicist's masterpiece, utilizing dense matrices to describe a single, unified delocalized electron cloud. While Pauling won the immediate popularity contest, Hückel was initially ignored for being too mathematical. However, time revealed the ultimate truth: Hückel's rigorous framework was fundamentally more accurate and predictive. It took 20 years for chemistry to finally catch up to his math, proving that Hückel's complex equations captured the true nature of molecular reality far more deeply than Pauling's intuitive sketches. In Integrity in the Darkest Era, we witness the profound moral courage of Erich Hückel. Appointed to the University of Marburg in 1937, Hückel took a defiant stand, stubbornly refusing to align with or support the Nazi dictatorship. This integrity came at a severe professional cost. While politically compliant peers were promoted, Hückel's research funding was stymied and his advancement deliberately blocked. For 24 years, he was kept in the subordinate rank of extraordinary professor, finally achieving a full professorship in 1961, just 1 year before his retirement. Yet, while his academic rank remained a flat line, his scientific legacy gained global traction. Hückel's story serves as a powerful testament to a man who prioritized his principles over his career. Welcome to The Late Vindication, the concluding chapter of Erich Hückel's remarkable journey. After decades of being overlooked, the 1950s marked a global awakening to his brilliance. From William von Eggersdorf officially popularizing Hückel's rule in 1951 to receiving a staggering 32 Nobel Prize nominations, Hückel's genius finally became undeniable. He was honored with the Otto Hahn Prize in 1965 for his dual mastery of physics and chemistry and was elected to the Royal Society in 1977. Though the ultimate Nobel Prize eluded him, these late accolades reflect a legacy finally brought into the light, a definitive triumph of rigorous science over skepticism, securing his rightful place as a permanent giant of the quantum world. Welcome to the modern Renaissance, where we witness the enduring legacy of Erich Hückel in the digital age. This final chapter illustrates how Hückel's theoretical groundwork evolved into the bedrock of computational chemistry. In 1962, pioneers like Hofmann and Lipscomb expanded his vision into extended Hückel theory to map complex 3D reactions. But the journey doesn't end there. Today, we are entering the frontier of quantum computing, where Hückel's molecular orbital theory is being executed on cutting-edge NISQ-era hardware. From drug discovery to advanced materials science, Hückel's math remains the vital link between quantum theory and technological innovation. What began as pencil and paper equations now drives the silicon and quantum processors of the future. As our journey concludes, we honor Erich Hückel, the man who gifted chemistry a transformative new language. Hückel's legacy is a masterclass in 3 dimensions: conceptual, changing our vision of electrons from static dots to delocalized clouds; methodological, proving that elegant simplicity can master complex systems; and ethical, championing scientific integrity over political pressure. He stands as the enduring bridge, seamlessly linking the abstract laws of physics with the tangible mysteries of chemistry. Hückel's life reminds us that the quest for understanding is a permanent frontier. As the closing quote suggests, the most vital act a scientist can perform is to never stop questioning the nature of our world.